For this video, we will be looking at the Dagpunar textbook for Monte Carlo Simulation. And for the first problem that we have in the book, what we are going to do is generate 1,000 random normal deviates so that we can estimate the integral of e raised to the negative x squared times the absolute value of cosine of x, and instead of Maple we will be using MATLAB. So entering into MATLAB, we created an M file here that will show us exactly what this will look like. So generating 1,000 samples and setting a border between -3 and 3, we can see that there is a slight bump at the beginning at about 1.5. It goes up to 0 all the way up to 1 in the center, and then it goes back down and is symmetric along the y-axis. So that is the generation of 1,000 random samples from -3 to 3, but in this case what we'll be looking for is the complete integral from -infinity to +infinity. And to do that, we will go ahead and solve it with 1,000 samples, as it says, and we'll be generating those random normal variables. Now, after doing some work on the integral, we were able to simplify it and include the random number generator so that we can multiply that, finding the expectation of the function cosine of x over the square root of 2. And running that, we can see that the actual value of this using MATLAB is 1.40, and our mean that we came up with was 1.40, quite nearly when we're rounding up. And we can also see, after solving for the standard deviation and recognizing what our n is, the upper control limit to be 1.42 and the lower control limit to be 1.37. Now, moving on to the second sample problem, we will be also looking for a confidence interval, and this time we'll have a double integral from -infinity to +infinity, and we'll have this function which we'll also need to do some substitution beforehand so that we can solve that. And in this case we would have z equaling y minus 1. So going to the problem, we can see that we'll be generating more random normally distributed numbers and then solving for the mean and standard deviation as in the previous problem. And running this, we can see once again an actual value using the integral 2 function inside of MATLAB, which gives us about 6.29, while our solved for value was 6.31 using 100,000 randomly generated numbers. And we can see within our very large control limits that the actual value is well between those and right about in the center, right close to our mean value. Thank you for watching.